So last time we introduced this notion of the Laplace transform. And the idea is you're starting with a function f of t, and you're going to produce a new function f of s. So the Laplace transform is essentially a rule that says how you take a function and make a new function. There's lots of ways you can do this. There's many, many choices out there. And so the way that this one works is it says, well, it's going to involve an integral from 0 to infinity, e to the minus st f of t dt. And because you're integrating with respect to t, at the end, there's no t left after you evaluate. But there will be something involving s, which is why the end result depends on s. It's a function of s. And you might say, well, why this particular one? And I guess the short answer is because it works. It does some really nice things. We've just sort of started dipping our toes in it, but one of the things that we're going to see is some of the things that show up in differential equations. So for instance, derivatives translate over nicely into what happens when you do the Laplace transforms. In particular, derivatives translates into a very simple algebraic operation. So it's like, oh, so it's like turning our differential equation problems into algebra problems. Yes, that's the whole punchline. That's what we're going for. Now, the way that we do Laplace transforms is we almost never use the integral because that's hard. Instead, we say, look, let's build up a collection of rules. And then the rules will tell us what to do. Now, there's sort of two categories for rules. One are basic functions. So functions we talked about, things like 1, a power of t, exponential, sine, cosine. We mentioned sinh and cosh. These are actually not that key, because sinh and cosh are basically just exponential functions. So, all right, well, that's an example of rules that are functions, but there's also other things which you can do. And, well, we didn't write them down. Well, let's write one of them down right now. Okay, suppose, let's test your memory. I take the Laplace transform e to the ct times f of t. So now I'm multiplying my original function I'm putting in by this exponential function. What's the effect? What happens? It shifts. In particular, f of s minus c. So we say, okay, so now we recognize that, okay, this is an example of the other type of building block, which are the rules. There's one other rule we mentioned last time. I won't write it down, but I won't write down the whole rule, but we'll just make a little note, which is to say this is linear. And that's just a nice way of saying it breaks up nicely over addition, and you can pull out multiplication. Now, we're going to have sort of two goals over the next several lectures. One goal is to keep expanding our list, have a few more rules, have a few more functions. Not that many more functions, actually. I think we have 2 more functions, and the next thing we're going to do is one of them. And but we'll have a few more rules. And then we're going to start seeing how to apply. All right, well, let's start with our next function. Okay. So our function, we're going to add to our list. It's called the unit step function. And when I took the course, it was called the Heaviside function. Now, when you see the function, we'll do a quick sketch of it here. What does it look like? Well, it looks in the following way. Namely, your 0 up until time 0, and then your 1. And I thought, Heaviside, that's a perfect name, because there's one side which is heavy. And I thought, brilliant name. But no, actually it turns out that's just the person's actual name. It's like Oliver Heaviside. Okay, coincidence is great. You know, we'll take it when we can. There was actually a mathematician whose name was Licorice. And he came up with sort of this idea of a certain type of operation. And they said, well, we'll call them Licorice Twist. And I think, that person was made to be a mathematician. Great names, great names. All right, so this is the unit step function. Now, what is this function really about? What I like to think about this is a function which is an on-off switch. That's what the unit step function is about. You're either on or you're off. And so here, you say, okay, we're off until time 0, and then we're on. That's it. And it says, okay, so why do we like on-off switches, on-off functions like this? And the key idea here is that this is going to be our tool for dealing with what we call piecewise functions. Now, what are piecewise functions? Those are functions when you say, in one range of inputs, I do this, then the next range of inputs, I do that. And it just depends on where you're at. I always like to say, well, I'd like to write down a single equation that captures all of it. So, looking ahead, this is an example of a piecewise function. But it's like, well, I don't want to have like a collection of rules. I just want to write it down as a single expression. And these step functions, that's what will allow us to do that. Okay, all right. So, what's our goal? Well, our goal is, let's figure out what happens when we take the Laplace transform of our step function. Now, this subscript use of a of t, you'll see it from time to time. I have fallen into the habit of more often just using it as u of t minus a, but depending upon where you're at and what you're looking at, the problem, you might see a subscript. So that's just for your information. Well, if we want to find our Laplace transform and we don't have any other facts, what do we do? Guess? Well, that's not the worst thing in the world. So, if we don't have anything, that's when we go back to our definition. And we don't have anything. So we say, all right, definition it is. Hello, definition. All right. So, we're taking our Laplace transform. And I'll write it as t minus a now. Well, that's definition, integral 0 to infinity of e to the minus st u t minus a, because that's our f of t. And we need to integrate that. But let's think about what's happening. So this is an on-off switch. So what's happening before a? We have 0, right? Before a, we're in the off position. What's happening after a? We're on the on position. And so, one way we can think about this, we say, this is really 0 for t less than a, and it's e to the minus st for t above a. Now, we don't actually care about exactly a. It turns out it's considered on, but that's not important. So how does that change our integral? What can we do to our integral to simplify it?
Change the bounds.
The bounds. Okay, what should our bounds be? A to infinity. So what happens from the part from 0 to a? Goes to 0. So we say, okay, well, using that, this is the integral a to infinity of e to the minus st dt. And now, that looks a little bit simpler. Okay, so that's how we use our on-off, right? We just say, okay, what's it doing right here? All right, well, do we know how to integrate that?
Yes.
Yes, we do. It's an exponential function. It's our favorite function in differential equations. What is that integral? So remember, we're integrating with respect to t. And we know we're integrating with respect to t because of the dt. How do you treat this minus s? That's our constant. So if you have e to a constant t and you integrate the effect, you divide by that constant. So the negative becomes a negative. I minus, we'll put it out front. Negative 1 over s e to the minus st, evaluate from a to infinity. Well, okay, what happens when you plug in infinity? 0. So we get 0, subtract. What happens when we plug in a? Well, we have that constant, negative 1 over s, and e to the minus sa. So we end up with, altogether, well, all right, as e to the minus sa, I'll put as, just that seems like alphabetical order over s. All right, so there we go. There's our new rule. In fact, we're going to expand on this rule next week. And next week, we're going to say, well, what happens if I have our step function times an f of t? And we'll figure out what happens. Spoiler alert, e to the minus as will play a role. But, that's for next week. Okay. So, let's do an example. Find the Laplace transform of f of t, where f of t is this piecewise function. It's 0 if we're between 0 and 1, or above 3. It's 3 if we're between 1 and 2. And it's 7 if we're between 2 and 3. And there's a note there that says, don't worry about endpoints, because when you do an integration, what happens at a single point doesn't matter, at least this week. There's another story coming next week. But the moral is, we don't really care what happens at the endpoints. So let's sketch this function. Well, it's not going to be too hard to sketch. We have a few critical points, 0, 1, 2, and 3. All right, and we say, all right, what's the behavior? Now, where it's 0, between 0 and 1, all right, so it's 0. It's also 0 if we're above 3, great. We're at 3 between 1 and 2. Okay, so here, this will be 3. And then we're at 7 between 2 and 3. Okay, so there's our picture. We're taking a few steps up and then back to 0 again. I'm going to ask a question. I haven't said this yet, so now is a wonderful time. What happens below 0, and do we care? I like that answer. Don't know, don't care. Very, very millennial. Don't know, don't care. All right. But that is actually the right answer. We don't know what happens below 0. Why don't we know? Because it doesn't tell us what happens below 0. Why don't we care what happens below 0? There's something actually subtle here. Why don't we care what happens below 0? It's not part of our function. That's true. But for some functions, we want to have it. Go back to the Laplace transform. As far as we care about, where do we care about our function? 0 to infinity. So what happens before 0? Doesn't matter. It can be whatever it wants. Doesn't even have to be defined. We don't care. The Laplace transform only cares what happens when you're greater than or equal to 0. All right. Okay, so now back to this problem. So what can we do? Well, there's two ways to do this one. We can actually go and just do the definition, pull out the definition of the Laplace transform, or we can use what we just learned. Do you have a preference? Yeah, let's use what we learned. Okay, so when we're using our step functions or the Heaviside function, the key is to ask, where does a transition occur in behavior? So where do transitions occur? There's a transition at 1, 2, and 3. So that says that when we're describing our function, we're going to have 3 transition points. So now what we do is we just start at the very beginning. And it's a very good place to start. How do we start? What's the behavior? 0. So our function, f of t, is 0. Okay, then we're going to add. Now, we have a transition at 1. So that says we turned our switch on and off at 1. So that introduces a u of t minus 1. That just says we're doing a change in behavior. And now the question is, well, what change in behavior? Well, the way to figure it out is you say, what's the new behavior? Subtract the old behavior. So what's our new behavior going to be? 3. What was our old behavior? 0. So you put in 3 minus 0. Okay, so we'll just make a little side note here for reference here. U t minus a. What's behavior after a? Subtract what came before a. That's the idea. Okay, so where's our next on-off? 2. So we add a u t minus 2. Okay, what are we doing after 2? 7. What are we doing before 2? 3. So we're going to take 7, subtract 3. Now we come to our last one. It happens at 3, u of t minus 3. What's our behavior after 3? 0. What's our behavior before 3? 7. So it's 0 minus 7. Now the claim is, that's it. They might say, how does that work? Well, let's just pick a point. 1.5. Let's say I'm 1.5. Okay, so if I'm 1.5, what's happening with these last two pieces? They're 0. So at 1.5, they're not there. We can cover them up. Then we have 0 plus 3 minus 0, because this is on, and so we should be at 3. Suppose we're at 2.5. Then we have one more switch that's turned on. Well, that means that this is on, that part is gone. Well, look, the 0 minus 0, they cancel. Well, that's not very impressive with 0. But the 3 and the minus 3 are canceling. And what are you left with? Is a 7. And now if you're all the way out here, say at 4, everything's on. The 3 and the minus 3 cancel. The 7 and the minus 7 cancel. This 0 and that 0 cancel. And the only thing that's left is that 0. So that's why it works. It's this sort of cascading thing. So if you have a piecewise function, you just have your on-off switches. And then you say, what happened before the on-off switch? What happens after the on-off switch? Take the difference. And that'll always work. Okay, so cleaning this up. This is 3 u of t minus 1 plus 4 u of t minus 2 minus 7 u of t minus 3. So we found a way to write our function, instead of our usual piecewise notation, just as a single line. All right, are we done? No, we're not. Because what was our goal? Yeah, find the Laplace transform. What we've done is we said, well, let's rewrite it in a way that's more Laplace transform friendly. So now we say, all right, let's take the Laplace transform. So Laplace transform of f of t. We can use the fact that the Laplace transform is linear. So that would be 3 Laplace transform u of t minus 1 plus 4 Laplace transform of u of t minus 2 minus 7 Laplace transform u of t minus 3. Well, what is u of t minus 1? The Laplace transform of that. So that's a equals 1. So that's 3 e to the minus s over s. Plus 4, what comes next? e to the minus 2s over s. Minus 7, last one, e to the minus 3s over s. Now, that's perfectly fine. You could, if you wanted to, say, oh, they all have a 1 over s in them. Pull it out. So 1 over s times 3 e to the minus s plus 4 e to the minus 2s minus 7 e to the minus 3s. And there you go. All right. Good. Any questions on that? We'll definitely get a lot more practice because these Heaviside functions, step functions, do show up a lot, particularly as we go into next week. Okay. Well, so let's do some practice. So we want to practice two things. We want to practice finding the Laplace transform, and there's a suggestion. And the suggestion here is you want to make sure that when you're finding the Laplace transform, look for ways to rewrite in terms of functions we already know. Now, what does that mean? Well, it's saying if you're going to find the Laplace transform of something, make sure your somethings look like things from your table. So you really are saying, I'm using my table here. So you say, okay, so for example, the 5, well, that's just a constant. That comes out. Does e to the 2t look like anything on our table? Yeah, it's right on the very edge, e to the ct. So it's like, okay, that's cool. Cool. How about the t cubed? Does that look like anything on our table? Yeah, t to the n. So we say, great. So now for the first one, we say, well, use linearity. So 5 Laplace transform of e to the 2t plus the Laplace transform of t cubed. And we use our table. We say, okay, well, e to the 2t becomes what? 1 over s minus 2. So this becomes 5 times 1 over s minus 2. And t cubed becomes what? So yeah, so whoops, that's not, should be a plus. It's a very thick plus. Okay. Yeah, so n equals 3, so 3 factorial, 6. You just write as 3 factorial, and then 3 plus 1 makes 4. All right, well that one was pretty easy. Yeah, they don't have to be hard. All right, let's look at our next one. Okay, t squared plus 10 sine 4t cosine 4t. Now t squared, is that on our list? Yes, so that's, life is good. Sine 4t cosine 4t, is that on our list? No, not yet. Now we could figure it out, but that sounds like work. We want to avoid work. That's why we have our table. So we start saying, okay, the tip here says, can we rewrite it? Is there a way to rewrite sine 4t cosine 4t? Double angle, okay, so what's the double angle going to tell us? So we look at this and we're like, double angle, which says sine of 2 theta is 2 sine theta cosine theta. All right, and we know that formula because why? It's on the formula sheet. Okay, so what does this 10 sine 4t cosine 4t become? What? There'll be a sine of 8t, and the coefficient will be 5. So I can pull the 5 out, and then we take the Laplace transform of sine of 8t. Okay. Well, what's the Laplace transform of t squared? Is it 2 or is it 2 factorial? Yeah, same thing. All right, that's okay. Good. Over the power s cubed plus 5. Okay, sine of 8t will become what? Yeah, 8 over s squared plus 8 squared. So if you're fans of squares, 8 squared is 64. Now you could, of course, write this as 2 over s cubed, and 5 times 8 is 40 over s squared plus 64. And there you go. All right, good, good. Now, that's examples of finding the Laplace transform, but we also need to find the inverse Laplace transform, which, if we haven't said it explicitly, is what that means when you see that -1. That's the inverse Laplace. We're sort of undoing. And there's another tip here. Wow, lots of tips. Is when you're finding the inverse Laplace, look at ways to rewrite, pull apart in terms of the functions we have seen. So there's really not even a formula for the inverse Laplace. So the only chance you have is to say, how can I make this look like something that we've seen? So for example, this 3 over s plus 4. We start scanning the table. Does it look like anything that we've seen? Yeah, it fits this mold. So I like to say mold because I'm saying like, okay, I'm trying to make it look like that. Now, if I were trying to make it look just like this, what are some things I could do? I could pull out the 3. That's allowed because things are linear. Now, another thing I can do is if I want s minus something, I could write this, instead of s plus 4, I could write it as s minus what? Minus 4. And now it's like, I fit the mold. Okay, so what does that become? It becomes e minus 4t. All right, well that one wasn't so bad. Okay, how about this one? Inverse Laplace, 9s minus 7 over s minus 1 squared plus 16. Does it fit a mold? I mean, I heard someone say that it fits a mold, but not exactly. It's like, we're kind of close, but we're also not kind of close. Which ones are you eyeing? It's like, I've got my eye on 1 or 2 of these. Yeah, a lot of you are eyeing this one, right? But, it's like, hey, you guys are neighbors. I'll also just sort of keep my eye on you as well. Okay, so what do we need to do? So remember, our goal here is to say, try to make it look like something. So downstairs, we have our s minus 1 squared. That's cool. 16, that's 4 squared. All right, good. If I have an s minus 1 squared downstairs, I either want a constant upstairs or an s minus 1 upstairs. Okay, so we have an s upstairs. So we're like, okay, let's sort of put on our s minus 1 hats. So we think about this for a second. We say, all right, another way to look at this. Let's pull a 9 out, and I'm going to times it by s minus 1 because I want s minus 1. And you're going to look at me and say, Steve, that's just not true. That's not equal to 9s minus 7. And I agree. But I haven't finished writing yet. What do we need to do? Plus 2. Right? So we're saying I needed to have something like an s minus 1 upstairs given this s minus 1 squared downstairs. Now it's like, okay, that's cool. But unfortunately, it doesn't really fit either one of these now. So what can we do? Pull it apart. Yes, also known as algebra. You know, that's what algebra is. It's the art of rewriting things so it's easier. Okay, so inverse Laplace. And I'm just going to pull it apart. I'm going to separate it upstairs. So I'm going to have one piece and then another piece. So the first piece will be, I'll pull out the 9 in front, s minus 1. S minus 1 squared plus 4 squared. And then the second piece will be 2, 1 over s minus 1 squared plus 4 squared. All right, are we ready to write the answer down? Does this one fit our mold now? It does. So according to our mold, what does this become? E to the t cosine of 4t. And this one? Ooh, I like that. Somebody noticed something. So what do we need to do here? Have we fit the mold as it's written here? No. What do we need upstairs? A 4. So what should we put? We should put a 4 there, right? But if I put a 4 there, I need to compensate for putting a 4 there. So we'll divide by 4. So we'll have a 1/2. And then everything else, very similar. E to the t sine 4t. And there we go. All right, good. Any questions? Well, then that means you're ready. We're due. We should have you do a problem. Actually, we'll have you do 2 problems. Okay. Find the following. The Laplace transform of 5 plus 2 times t e to the 3t, and the inverse Laplace transform of 16 divided by 2s plus 1 cubed.
5 over s.
Okay, starts out as 5 over s. I agree with that. Plus, good move.
S over s minus 2 times s minus 3.
2 times s minus 3? What's the right mold? Which one? What's the mold here? E to the ct, t to the n. What's t? What's n? 1. Okay, what's c? 3. So she would have 1 factorial, also known as 1. S minus 3 to the 2. So this should be, and then there's a 2 here. So this should be 2 over s minus 3 squared, yes? What's the difference between what and where?
The Laplace transform that is e to the ct, t to the a, right below.
Right?
What's the difference between those two?
Well, n here is a whole number, like 1, 2, 3. A here is any number. N factorial is relatively easy to compute. Gamma of a plus 1 will give you nightmares. So that's the difference between those two. Well, you're right. We're going to get into that next week. Yeah, we haven't learned about that rule. Oh, that's a good rule. We're going to have some really beautiful things. So we're going to keep increasing our rules, and the more rules we get, the more options we have. Okay, how about this one? Inverse Laplace transform, 16 over 2s plus 1 cubed. Do we have an answer?
2e to the negative 1/2 t.
Sorry, what?
2e to the negative 1/2 t times t squared.
Okay, so I've heard 2e to the negative 1/2 t squared.
Yes.
Okay. Are there other answers?
Same thing, but with no 2.
Same thing, but without a 2. Okay, are there other answers? Same thing, but a 4 in the front. Someone has said, let's throw an 8 just to be, respect all our powers of 2. Okay. One of these is probably right. Let's think about it. Okay, so first off, trying to fit the mold, which one comes closest? It looks like this one comes closest because there's some power of S downstairs. What are some things that we need to fix? Yeah, the 2 is a problem. So how do you fix the 2? Well, you have to be careful, not just a half. So I'm going to think about pulling a 2 out. So if I pull a 2 out, it's not just really a 2. What is it? It's really an 8, right? It's a 2 cubed. And then S plus a half cubed. Okay, so we're now up to the following. We have our 2, because 16 over 8 is 2. Now we're really close here. S plus, we can write S minus a half cubed. Now the question is, are we now matching? Exactly. Okay, someone's like, we're very excited. Throw an exclamation mark. Turns out that 2 and 2 factorial are the same. Do we exactly match? Yeah. For the value of n equals 2 and c equals negative a half. So there's going to end up being no constant, and that's the right answer. So e to the minus 1/2 t times t squared. All right. Well, good. Practice, right? The more we practice, the better we get. Okay. Well, now for something a little different. We're going to talk about why we like Laplace transforms when it comes to differential equations. So the question is, what happens when you take the Laplace transform of a derivative, and does it do something nice? So we say, okay, no problem. We can always go back to our definition. So we're taking the Laplace transform of f prime of t, and well, all right, so that's the integral from 0 to infinity e to the minus st times f prime of t dt. And now we say, well, we have our wonderful tool from Calc 2, integration by parts. It's one of the first things we learned about when we talked about integration techniques. And we say, all right, we'll do a u dv break apart. So, of course, the integral of f prime is f. So we have our uv minus the integral of v du. Well, we can evaluate from 0 to infinity because as you go to infinity, the exponential term drives everything down to 0. Then when you plug in 0, you get your f of 0. So that's where your f of 0 is. The minus is because you subtract plugging in 0. All right, so that's the first part. So the evaluation of the first part leads us to there. Now the second part says what? Well, we had an s and a minus s that comes out, so that's where the plus s is coming from. And then we have our e to the minus st f of t dt. And we're like, wait, we've seen that before. That's the Laplace transform of f of t. So what's the punchline? So the real thing that comes out says, oh, if you're taking a derivative, it becomes multiplying by s. So that's why we say this idea of derivative becomes an algebra thing. There's an algebra lurking in the background, waiting for us. Now you can do this many times. If you do it twice, you can say the Laplace transform of f double prime becomes s squared, Laplace transform of f minus s times f of 0 minus f prime of 0. And you can actually do this any number of times you want. So if I want to take the nth derivative, we never go past the third derivative, but you could. You get, the s to the n times the Laplace transform of just f minus s to the n minus 1, f of 0, s to the n minus 2, f prime is 0, and you keep working your way through. So your powers of s keep going down, and then where you evaluate, here it's a function, here's the derivative, and it'll be the second derivative, and so forth, until you get to the end. All right, so let's do an example really quickly. Suppose we have x double prime, and I didn't write things down, so let's write something down. What number do you want here? 6x prime and 5x. We're not going to solve. Don't worry. We don't have to worry about crazy roots. Equals e to the 2t sine 5t. And we happen to know that our initial conditions are x of 0 and x prime of 0 are both 0. And the question is, find the Laplace transform of x. Now, keep in mind, here, this x of t, this is our solution. It's saying, find what the Laplace transform is of the solution. And it's giving us the problem. Now, there's two ways to do this. One is you could actually literally find the solution, which I strongly discourage right now, because that ruins the whole process. But the other way is to say, let's use the tools. So the tools are, let's take the Laplace transform of the two sides. So Laplace transform of x double prime plus 6 Laplace transform of x prime minus 5 Laplace transform of x. Notice here we're using linearity. So I'm taking the Laplace transform of the left. That has to equal the Laplace transform of the right, e to the 2t sine of 5t. Well, now we say, well, hey, Laplace transform of x double prime, that would be s squared times the Laplace transform of the function. Well, so that's our s squared x of s minus s times what happens at 0. In our case, that would be 0. Minus what happens to the derivative at 0, which in our case is 0. Okay, so that's the first part. Plus 6. Now we take the Laplace transform of just x prime. So that would be s, the Laplace transform of x, which is x of s. Then we're going to subtract what happens at 0. And what happens at 0? 0. Then we're going to take minus 5, the Laplace transform of x, which is x of s. So I'm applying the rules to each piece. Now that's the left-hand side. On the right-hand side, this equals e to the 2t sine 5t. Well, what do we do to do that? We look at the sheet. Exactly. We are going to learn to use our tables. And we say, e to the 2t sine 5t, well, that's given to us. We just copy it. So in this case, we have c equals 2, b equals 5. So that would be 5 over s minus 2 squared plus 5 squared. All right. We're almost done with this problem. What can we do? Well, upstairs, on the left-hand side, factor the x of s out. So you get s squared plus 6s minus 5 times x of s. And that's going to be equal to our 5 over s minus 2 squared plus 5 squared. Now, our goal was to find this. We're almost there. What is left for us to do? Move that other part across. So x of s is 1 over s squared plus 6s minus 5 times 5 over s minus 2 squared plus 5 squared. So now we found the Laplace transform of our answer. If we wanted to get our answer, what could we do right now? We could take the inverse Laplace transform of that. But that looks messy. We need some more tools, like partial fractions. which is what we'll do next time, because our time is up for today. All right, have a good day.